video, we are going to unpack the fundamental principles of thermodynamics and its first law. Let's go. In the following, we will address the following points. First, we start with an introduction, then we turn to the chapter 1 entitled Fundamentals of Thermodynamics, where we develop these points. After this, we pass to the second chapter, first law of thermodynamics. Ever wondered why an ice cube melts in your hand or how a steam engine works? The answers lie in thermodynamics. In these chapters, we will be unraveling the mysteries of energy and its transformations. We will start by laying the groundwork, exploring the key concepts and terminology of thermodynamics. Then we will delve into the first law, a cornerstone of the field that describes the conservation of energy. Join us as we uncover the fascinating world of heat, work, and the laws that govern them. Chapter 1. Fundamentals of Thermodynamics. At the end of this chapter, the learners will be able to first, discuss the elements and boundaries of thermodynamic system. Second, evaluate the concept of equilibrium. Third, get to know the perfect gases laws. Thermodynamics is a science that emerged in the late 17th century. At the time, the focus was on building machines that were essential for the nascent industry. It is reported that Denis Papin, which is a French physicist, came up with the idea of building a machine using water vapor after observing boiling water in a container. Seeing the steam lifting the lid, he realized that it could also push a piston and thus provide work. The initial motivation was therefore to meet an essential industrial need at the time, to find the optimal condition for converting heat into work. Thermodynamics can be divided into two terms: thermo, which means heat, and dynamics, which means force. Definitions and concepts. What is a system? A system is anything kept in consideration. Surrounding is everything which is external to the system. Boundary is the envelope which separates the system and the surrounding, since the universe is equal to the sum of the system and surrounding. Systems can be classified into homogeneous and heterogeneous systems depending on the material contained. Depending on the exchange with external environment, systems can be classified on open system, closed system, and isolated system. A system is in equilibrium if it does not undergo any evolution and function of time, when external actions do not vary, and when there is no transfer of matter or energy between the system and surrounding. Transfer of energy in the form of heat, denoted Q, or mechanical work, denoted W. Per convention, the quantities received by the system are counted positively, and the quantities transferred to the external environment are counted negatively. Thermodynamic process. A transformation is a variation of parameters. An isochoric transformation is a transformation at constant volume. An isobaric transformation is a transformation at constant pressure. An isothermal process is a transformation at constant temperature. And an adiabatic transformation is a transformation in which there is no exchange of heat with surrounding. State of matter. Depending on temperature and the pressure conditions, all bodies can be in one of three states: solid, liquid, and gas. Transition from one state to another is a change of physical state or change of phase. Perfect gases. A perfect gas is a collection of molecules that do not interact with each other except through elastic collision and that occupy the maximum volume available. It obeys the equation of state PV equal to nRT. Among the laws that govern ideal gases, there is Dalton's law. Here, a solved example of how to use this law for a mixture of gases. Chapter 2. The first law of thermodynamics. At the end of this chapter, the learner should be able to discover the first law of thermodynamics, calculate work, heat, enthalpy, and energy. Apply the first law to perfect gases and chemical reactions. The first law of thermodynamics is a fundamental principle that governs the behavior of energy. It's essentially a statement of conservation of energy, which asserts that energy can't be created or destroyed, only transferred or transformed. Internal energy. The internal energy of a system is its energy content. At the microscopic level, the system's internal energy is defined as the algebraic sum of the kinetic and potential energy of all particles in the system. Work is defined as the transfer of energy that occurs when a force is applied to an object, causing it to move in the direction of the force. Heat is characterized by variation in the system's temperature or change in the physical state of the system matter. Heat is a special form of energy. Heat always flows from a hot source to a cold source. Heat is a path function. Mass heat capacity is the heat required to raise or lower by 1 degree temperature of 1 kilogram of a system. Calorimetry is an experimental method for calculating the heat of a reaction, the heat capacity of body or latent heat of fusion. Latent heat of change of physical state is the quantity of heat needed to change the physical state of 1 mole or gram of matter at constant temperature. Statements of the first law of thermodynamics. Energy released in one place must be gained somewhere else. Furthermore, because energy can be changed from one form to another, the energy lost by one system can be gained by another system in a different form. For example, the energy released by burning coal in a power plant may ultimately turn up in our homes as electric energy, heat, light, and so on. There is a thermodynamic function of a system called enthalpy, which is defined as H equal to U plus PV. Application of the first law to ideal gases. If the heat is constant, internal energy U will equal to QV, which is NCV delta T, enthalpy delta H equal to QP, which is NCP delta T. We use also the Mayer relationship for perfect gases and the Laplace coefficient gamma. Here, synthesis table summarizing how the first law is applied to ideal gases, enabling us to calculate work, heat, internal energy, enthalpy for different thermodynamic systems. Application of the first law to chemical reaction. At constant volume, Q would equal to delta U. If Q is less than 0, the reaction is called exothermic. When Q is upper 0, it's called endothermic reaction. When Q equals 0, that means a thermal reaction. At constant pressure, Q is equal to Qp, which is delta H. For chemical reaction, we can deduce a relationship between Qp and Qv. As we conclude our exploration of the fundamentals of thermodynamics and the first law, it's clear that these concepts are essential for understanding the world around us, from the engines that power our cars to the stars that light up the night sky. Thermodynamics plays a vital role. As you continue your studies, remember that thermodynamics is not just a subject for textbooks, it's a tool that can help us solve some of the biggest challenges facing our planet. So, see you in the next video. Don't forget, subscribe, like, share for more educational content. Thank you.